From Canada's Perimeter Institute for Theoretical Physics, welcome to Perimeter Explorations, classroom videos that investigate the frontiers of science. Join narrator and physicist Damien Pope of Perimeter's outreach team and leading scientists and engineers as they take you on an educational journey of wonder and discovery.
Things are unexpected, surprising.
Einstein once said, the world cannot be that crazy. But today, we know it is that crazy.
The real world is a lot stranger than any science fiction I've ever seen.
Understanding it is a major challenge.
So, what do you know about physics?
Just aced a test on it.
So?
It's the study of the nature of the world around us. Motion, forces,
Energy.
The physics of the everyday world is classical physics. So you're looking for a challenge.
sure.
Bring it on.
Follow me.
Where'd everyone go?
This challenge requires your full attention. No distractions. Ever heard of the double slit experiment? Step 1 of the challenge.
Tennis balls are classical objects. Let's see what happens when we fire some at the barrier.
What happened?
Some of the balls went through the slit and left marks on the wall at certain spots.
Right.
The distribution of marks on the wall lines up with a single slit. If we open the slit to the right, a similar distribution builds up.
What if both slits are open?
Good question.
With both slits open, we get the same distribution we'd get if we did the experiment with one slit at a time, then combine the results. But this result doesn't just happen with tennis balls. We could have used apples, shoes, or grains of sand, because all classical particles produce the same overlapping distribution. It's the trademark for how localized particles behave in the double slit experiment.
This is where I come in. You just did. See, dude? Dab your finger in the pool, will ya?
What pool?
The one right over there. Just one small tap. Cool. Nice.
The wave spreads out from its source.
Now it's your turn. Waves, man. Yeah.
With repeated waves, we see the formation of crests and troughs as the waves spread farther.
Now, both of you at the same time. Whoa.
When two waves overlap, they interfere with each other. When crests meet, they form an even higher crest. When troughs meet, they form an even deeper trough. We call this constructive interference. Places where it happens are called interference maxima. When a crest meets a trough, the two cancel each other out. We call this destructive interference. Places where it happens are called interference minima. The overall pattern alternates between constructive and destructive interference, between interference maxima and minima. This is called an interference pattern. Just as two waves interfere when they cross over each other, one wave produces the same interference pattern when it passes through the two slits.
That interference pattern is a trademark of water waves spreading out and overlapping.
Alright, but what about other waves? We're gonna do a double slit experiment with light?
Why not? Thomas Young did the first one with sunlight over 200 years ago.
What did he find?
You tell me.
Cool.
So, light produces an interference pattern too.
Everything we model as a classical wave. Light, water,
Sound.
yep.
All right. I think we've covered the necessary points about classical physics. In a double-slit experiment, particles produce a distribution of localized marks.
And waves spread out to produce an interference pattern.
Not enough of a challenge, perhaps?
Perhaps.
I'll take that to mean you're ready for a real challenge.
Sure. Sure.
Yes, we're ready.
Shall we?
Yeah.
Okay. Let's go. Now then, what can you tell me about the subatomic world?
The stuff that's inside of atoms.
Electrons, protons, and neutrons.
Let's start with electrons. Do electrons behave in the same way as classical particles? How might we find out?
A double slit experiment.
With electrons?
Why not?
Will the electrons form the same distribution that the tennis balls did?
Or an interference pattern like the water waves did.
Or?
Or what?
We were driven there by experiments and the desperate struggle to try to understand experimental results.
So we should be able to get the pattern a little bit higher, right? So maybe again the deflection plates?
Herman Battleline and his team at the University of Nebraska-Lincoln are performing the double slit experiment with electrons. It's the latest in a series of similar experiments dating back to the 1960s.
One of our goals was to be as close to the original thought experiments as we could possibly be.
The scale of the experiment is incredibly small. Each slit is only 100 nanometers wide. That's 1,000 times narrower than a strand of hair.
It takes a lot of time to get things lined up, a lot of patience to get things to work properly.